Hello everyone, in this video I'm going to give an overview of different object recognition tasks. So I will describe the objective of each task, including object detection, classification, and segmentation, and how these methods work, and as well as their performance metrics. So let's get started. So here are the 6 different object recognition tasks that we are going to discuss in this video. From left to right, the level of details that we extract from this task increases. So on the left, we have the image classification, which gives us image level information, including like what objects are in the image. But as we go toward the right, we get more information such as the bounding box around the objects in the image, or even further, we also get the segmentation mask of the objects. So let's start with image classification. The objective of image classification is to assign a single label or sometimes multiple labels to an entire image that identifies the main subject or subjects in the image. So image classification comes in 3 different flavors: binary classification, multi-class, and multi-label. So let's see how these methods are different. For binary and multi-class classification, we always assign a single label to the entire image. But the difference between binary and multi-class is in the form of question that we are trying to answer. For binary classification, the form of question is always in form of yes or no type of question, whereas in multi-class, we are trying to identify which object out of a set of options is present in this image. So given this example image of a horse, for binary classification, the question would be, does this image contain a horse or no? And the output would be yes. Whereas in multi-class, the form of question would be which animal out of these 3 different options, cat, dog, or horse, is present in this image. And we can always choose only one of them. So the output for this image would be a horse. Now in multi-label classification, we can assign a list of labels to an input image. For example, for this image, the type of question would be what animals out of cat, dog, or horse are present in this image. And we can choose multiple options. So for this example, the output would be a cat and a dog. So another difference between multi-class and multi-label is that so the probabilities that we get from multi-class classification, there are class probabilities, and they sum to 1. So for example here, Apple has the highest probability, but if you sum these probabilities, they will always sum to 1. But in the case of multi-label classification, these probabilities, there are the probability of the presence of that object in the image, and they do not sum to 1. So for example, here we have banana with 0.9, orange 0.7, and strawberry with probability 0.6. And as you can see, they do not sum to 1. So in order to get the class probabilities for multi-class classification, we can use the softmax function. So given a vector of z, which is the logits, that is the output from the neural network model, we can apply the softmax function, and then we get the probabilities for each class from class 1 to class c. And the softmax function is applied in this form, where we take the exponential of each element in the logits divided by the sum over the exponential of the logits. However, for multi-label classification, we have to treat each class as a separate binary classification, and we ask this question: does this image contain this class, yes or no? And to get the probabilities for this yes and no, we use the sigmoid function, which is 1 divided by 1 plus e to the power of negative zi, where zi is the logit associated for class I. So in order to build an image classifier, we can define a CNN, or convolutional neural network, that receives input image X, and it outputs logits Z, from those logits we can predict our label Y. And there are 2 approaches to train this model. Approach 1, we train from scratch. So in this case, the parameters are randomly initialized, and this is not recommended because it requires more training data. In the second approach, we use transfer learning, where we basically rely on some pre-trained models like ResNet that is pre-trained on ImageNet, and then we can just fine-tune the last layer of this model. Next, moving to the performance metrics for image classification. The first and most commonly used performance metrics for image classification is obviously the accuracy, which is defined as the number of correctly classified samples divided by the total number of samples. However, this method is not very suitable when we are dealing with imbalanced classes. And also, it doesn't provide information on the individual class performance. Another metric basically is to use confusion metrics, where for each of these ground truth classes, we can see how many of them are correctly classified, as well as how many of them are classified to these other classes by mistake. Another performance metrics for image classification is precision and recall. For computing precision and recall, first we have to identify all the samples into these four categories: true positive, false negative, and true negative. And this is treated for each class separately. Then we can calculate precision and recall with these formulations. Precision is true positive divided by all the predicted positive samples for that class I, and recall is the true positive divided by all the real positive samples for that class I. And while these are computed for each class separately, we can also average them in two different ways. A macro averaging, where we treat each class equally, and basically we give the same weight to all the classes, whereas in micro averaging, we treat each sample equally, and basically here we give a weight equal to the number of samples for that class. And another metric is F1 score, which is basically the harmonic mean of precision and recall, and it is defined as 2 times precision times recall divided by precision plus recall. And this gives us a balancing trade-off between precision and recall. The performance metrics that we have described so far are good for multi-class classification. However, for multi-label classification, we have different metrics. So the first metric for multi-label is 0-1 accuracy, or also known as the subset accuracy. In this case, we basically look for exact matches between the list of labels for ground truth and the list of labels that are predicted. And even if one of these the elements in between these two vectors are different, we consider this sample as the incorrect prediction. The second performance metrics for multi-label classification is called Hamming accuracy, where instead of looking for the exact match between ground truth and predicted vectors, it will count the number of correctly predicted labels. So in this case, for example, 4 out of 5 labels are predicted correctly. So the performance associated for this image is 4 out of 5. The next performance metrics for multi-label classification is Jacquard similarity, also known as intersection over union. For Jacquard similarity, we basically calculate, we find the intersection over ground truth labels and predicted labels divided by the union of these ground truth and predictions. So for example, for this image and these predictions, the ground truth labels are strawberry, banana, and orange, but the predictions are apple, banana, and orange. Therefore, the intersection is banana and orange, so the size of the intersection is 2, and the size of union contains all these 4 labels. So finally, the Jacquard similarity is computed to be 2 over 4. Now moving to the next section for object localization. As we saw previously in image classification, the objective of image classification is to identify what object is present in the image. But object localization gives us more information compared to that, since not only it gives us which object is present in the image, but it also tells us where that object is in the image. So given an input image like this, object localization will provide the bounding box around that object in the image, and this bounding box is represented with 4 values, x1 and y1 for the coordinate of the top left corner, and x2 and y2 for the coordinate of the bottom right corner. So a major limitation of object localization is that the traditional techniques for object localization were only designed for a single object, and when we are dealing with multiple instances of an object in the image, they may provide an overall bounding box that contains all the instances. So that brings us to object detection, which is able to detect multiple objects from the same or different categories. So the goal of object detection is to find the bounding boxes around each instance of semantic objects such as pedestrians, cars, and etc. And the output, as output, we get a list of bounding boxes that can be represented with a vector of 4 values, x1, y1, x2, and y2. So this vector is for each bounding box. And each bounding box is also associated with an object class that represents, that indicates this bounding box contains this object. So here is an example output of object detection where the resulting list of bounding boxes and class labels are imprinted onto the image for visualization. So there are 3 common formats for representing bounding boxes. The first format is called Pascal VOC, or also referred to as XY. And in this format, we represent this bounding box with the top left corner and bottom right corner. Then we have the COCO format, or XYWH, which is represented with the top left corner and the width and height of the bounding box. And lastly, we have the YOLO format, which is known as CXCYWH, and CXCY represent the center coordinate of the bounding box, and WH are for the width and height of the bounding box. There are 2 types of object detection models. The first category is called 2-stage object detectors, which are based on region-based CNNs, or RCNN. In this category, first they try to find some region proposals, and then in the next stage, from those region proposals, they try to predict the final bounding boxes. And on the other hand, we have 1-stage object detectors where they predict the bounding boxes in 1 stage, and therefore they are faster. The first RCNN model works in 3 steps. So given an input image, first it computes 2000 region proposals using an algorithm called a selective search algorithm. Then it computes the features using a deep convolutional neural network, or CNN. So these features are computed for each region. And then in step 3, it classifies each region using a linear SVM and also performs a bounding box regression to find the bounding box. However, the major drawback for RCNN is that it has too much redundant computations. As you can see, given this input image, we compute about 2000 region proposals, and that means for one image, we have to run the CNN model around 2000 times, so 1 per region. Next, we will see how the RCNN model is evolved to reduce this redundancy. Here is the evolution of RCNN models. As we saw earlier, RCNN has too much redundant computations. Therefore, fast RCNN was proposed to reduce that redundancy by sharing the computations of features using a deep convolutional neural network. And then faster RCNN was proposed to further optimize the process. After that, mask RCNN was designed as an extension of faster RCNN for instance segmentation. So now let's see how these algorithms for object detection works. So moving to fast RCNN, it first pre-computes the feature maps using a CNN model, and these feature maps are shared among all the region proposals. Then it uses a mechanism called ROI projection for region of interest projection and ROI pooling layer to extract the features for each region proposal. Then after that, faster RCNN further optimized this process using a new subnetwork called a region proposal network, which predicts the region proposals using some anchor boxes. After that, similar to fast RCNN, it extracts features using a ROI pooling layer. And here is the architecture of faster RCNN model. So given an input image, we first feed this input image to a backbone network such as a ResNet 50 or a ResNet 101, and we extract features at different scales in the backbone, from the backbone. Then in order to make this object detection suitable for detecting objects at multiple scales, we feed these features at multiple scales to a feature pyramid network or FPN, and after that we use the RPN and ROI pool to extract to predict region proposals and extract features for each region proposal. And finally, we send the extracted features to a classification head and bounding box regression head. Now let's look at some performance metrics for object detection. In the first step, we need to map predictions and ground truth boxes into true positive, false positive, or false negative based on their intersection over union. So intersection over union, or IOU, is defined as the area of overlap between predicted box and a GT box divided by the area of union of the two boxes. And then based on this IOU, we can determine which predictions are true positive or false positive. So a true positive is a predicted box that is matched with a ground truth box in the same class and that is not assigned to any other prediction, and it has an IOU greater than some predefined threshold. After assigning predictions and ground truth to TP, FP, and FN, then we can compute precision and recall as shown here. So precision, similar to before, is TP true positive divided by true positive plus false positive. So that is the total number of predicted boxes. And recall is true positive divided by true positive plus false negative. So that is the total number of ground truth boxes. Another common metric for the performance of object detection is called average precision. In order to compute average precision, first we need to construct this precision recall curve, which is based on the confidence values. And then average precision is essentially the area under the curve of this precision recall curve. And it can be represented as this integral function. However, it's common to use this 11-point approximation, which is computing the average of precision values at these different recall levels from 0, 0.1 all the way to 1. Now moving to semantic segmentation. The objective of semantic segmentation is to assign a class label to each pixel in the image. Therefore, it is called pixel-wise classification. And this pixel-wise classification will effectively partition the image into multiple segments and provides a detailed comprehension of the scene, and allows us to distinguish different objects from the background. And it has several applications in medical imaging, autonomous driving, and scene understanding. And here is an example input and output of semantic segmentation. So given this input image, the semantic segmentation in this example is segmenting out all the horses and separating them from the background. One of the most popular neural network architecture for semantic segmentation is the UNet model. And the architecture of the UNet is shown here, which is composed of an encoder and a decoder. The encoder is composed of several downsampling layers for decreasing the spatial resolution of the feature maps, followed by the decoder layers for increasing the spatial resolution. Furthermore, there are these skip connections between the encoder and decoder layers in the same level. Now let's look at some performance metrics for semantic segmentation. Remember that semantic segmentation is essentially pixel-wise classification. Therefore, one of the early performance metrics is based on pixel accuracy, which is the number of correctly classified pixels divided by the total number of pixels. However, this measure has several drawbacks. That is, it doesn't have the symmetric property, it is biased toward predictions that are larger than ground truth, and also it suffers from imbalanced classes. Another metric is based on precision and recall for each class. So for each class, we first match each pixel into one of these four categories, and then we compute the precision and recall based on these equations. While these two metrics provide more detailed class level performance measures, however, they are still not symmetric. There are two symmetric measures known as IOU and dice coefficients. So to understand IOU and dice coefficient and their differences, IOU is intersection over union, so that means this area, the area of intersection divided by the union area between ground truth and predictions. Whereas in dice coefficient, we divide the intersection times 2 divided by the sum of ground truth segment area and the prediction segment area. In some applications, it's very important to capture the boundaries of segmentation masks very accurately. For example, here we have this ground truth segmentation mask of a horse, and these P1, P2, and P3 are predictions from 3 different models. And when we compare the mask IOU of these predictions, we see some marginal improvement going from P1 to P3, while we can clearly see that P3 has much better boundaries than P1 and P2. So that means mask IOU is not sensitive enough at the boundaries. But there is another metric called boundary IOU, which shows a significant improvement from P1 to P3. So that is 22% improvement from P1 to P3. So boundary IOU has more focus toward the boundary pixels of the predictions. So one of the limitations of semantic segmentation is that it cannot separate instances of the same class from each other. So when we want to separate those instances, we need to use instance segmentation instead of semantic segmentation. Instance segmentation combines detection and segmentation together, and therefore we are able to identify instances of the objects from the same class from each other, and we are able to segment those instances. However, we should note that instance segmentation is only applicable to countable things, but not stuff. So let's see what is the difference between objects or things versus stuff. Objects are discrete and countable things such as people, animal, cars, etc. But stuff are continuous areas like sky, grass, road, etc. So we should note that instance segmentation is only applicable to these countable things, so that we can segment or identify instances of these classes. Here is an example input and output of instance segmentation. In this example, we have 3 horses, and the horses are countable, but the sky, grass, and mountain range are not countable. So we can only apply instance segmentation to the horses. And therefore, in the output, we get this instance segmentation mask for each horse, but in addition, we also get these tight bounding boxes around each mask. Even if we remove these bounding boxes, since we are using different colors for each mask of the instances, we can separate the masks from each other. One of the most popular models for instance segmentation is called mask RCNN, which is an extension of faster RCNN. So we have already seen the architecture of faster RCNN using the backbone and this head for bounding box regression and classification. So let's expand this area and only look at one of these feature maps. Mask RCNN uses the exact backbone, region proposal network RPN, as well as the bounding box regression and classification heads. But in addition, it also adds this extra head that retrieves features from the regions of interest using ROI align, and then performs mask prediction in this new head. The performance metrics for instance segmentation is very similar to object detection metrics, except that instead of bounding boxes, we can also use the mask for determining this average precision. So for each class K, we can compute this average precision for class K with a given IOU threshold, and assign to do this, we assign the predicted mask to ground truth mask based on their mask IOUs and determine true positive, and false negative. Then we sort predictions based on their confidences and construct the precision recall curve as we did before for object detection, and then we calculate the area under the curve. So that would determine the average precision for class K based on this IOU threshold. In addition, we also have the mean average precision, which is essentially the mean of average precisions for all classes. As we have seen so far, semantic segmentation works on both things and stuff, so countable things as well as stuff, but it is not able to separate the instances of countable things from each other. However, instance segmentation only works on countable things, and it is able to separate instances of those countable things even if they are from the same class. Now, what if we want to do both stuff and things together? In that case, we have to use panoptic segmentation. So panoptic segmentation combines semantic and instance segmentation together. Each pixel is given the class label, whether this belongs to countable things or stuff. But in addition, if that pixel belongs to countable things, the instance of that object is also determined. So let's compare the outputs of these different segmentation tasks side by side. On the left, we have the semantic segmentation, where we can clearly separate the foreground classes from the background, but we are not able to separate the instances of this object class from each other. In the center, we have the instance segmentation output, where we are able to generate some segmentation masks for each instance of the class horse, and therefore we are able to separate them from each other. On the right, we have panoptic segmentation that works on both things and stuff. So not only we are getting these instance segmentation masks for each horse, but we are also getting the segmentation mask for this stuff like sky, mountain, tree, and field. The performance metrics for panoptic segmentation is called panoptic quality. To compute panoptic quality, first we need to match predictions and ground truth segments based on their IOU values, and this will give us true positive, false positive, and false negative sets for class K. Then we calculate PQ for class K with this formulation: the sum of all IOU values between prediction and ground truth areas for the true positive set divided by the area of the true positive plus half of the area of false positive plus half of the area of false negatives. The panoptic quality metrics can then be decomposed into these two other metrics called segmentation quality or SQ and recognition quality or RQ, and these formulations are given below them. This decomposition is very useful to gain further insights for error analysis. So that brings us to the end of this video. In this video, we covered several topics including image classification, which could be either binary, multi-class, or even multi-labels. Then we moved to object localization and detection to get bounding boxes around the objects in our image. And finally, we went over some segmentation tasks, including semantic segmentation that is not able to separate instances of the same class from each other, but instance segmentation was able to separate the instances from each other. And finally, we also covered panoptic segmentation that works on both stuff and things. So I hope that you find this video useful, and thanks for watching.